good. It's still alive. So, but looks like not many of you left. So let us recall what we discussed last lecture. We introduced the universal gravity law, and in both scalar and vector form. By the way, who will help me to formulate this universal gravity law?
Two objects with mass will interact with each other.
With gravitational.
With gravitational force.
Yes. So how? But let's say quantitatively, how we describe it? That is proportional. Gravitational force is proportional to masses of the objects, and reversely proportional between these objects. There always we need to remember about universal gravitational constant, which was determined experimentally later, like much later after the equation was derived. And yesterday we also described some prehistory and formulated the Kepler's laws, like 3 Kepler's laws. So today, as I mentioned last time, we will continue with Kepler's laws and will explain why actually they are like this, like they are, and what physics is behind it. And we will also try to combine 2 Kepler's laws with second law of motion in order to derive the universal gravitational law. So it's kind of back. We're going a little bit back because, if you remember, last time we did not derive the universal gravitational law, and we just introduced it as in final form and claimed that this is it. However, so that's what done in many textbooks, but it makes sense to go through these steps, which helped Newton actually to eventually come to the point when the universal gravitational law was formulated in its final form. So let us start first with the Kepler's laws. So what is the first Kepler law? What does it tell us?
Orbits are elliptic.
Exactly. So all planets are moving about the sun along some ellipse orbits. So that's something like this. Extreme case. By the way, what is the definition of ellipse? How would you define ellipse? So if let's start from easier. Start from circle. Circle is a geometric set of points which are equally spaced with respect to the center. So the radius is constant. What would you tell about ellipse? So the definition of ellipse will be that there is also some geometric set of points, each of which is placed in that way that the sum of distances to special points called focus of ellipse. So this is R1, this is R2. R1 plus R2 is constant. So this is the definition of the ellipse. And by the way, you know who proposed an easy way to draw ellipse and got accepted as a full member of Academy of Sciences of Great Britain when he was 13 years old. you heard about Maxwell equations, which describe features of electromagnetic waves. So that guy Maxwell, what he proposed, you put two nails in the focus, have a rope and a pen, so you can draw this ellipse, ideal ellipse, because the distance, the length of the rope is not changing, and that's how you can draw this ellipse in a simple way. So 13 years old, got accepted to Royal Academy of Sciences. But, well, later he proved that he was accepted not for nothing. He made a more fundamental contribution to science. So, what Kepler's law tells us, that in one of these, let us remove this, oops, we don't need this radiuses. So in one of the focus of ellipse, we have our sun. And here is the planet. So we have MS, and this is MP. And they are moving along this ellipsoid trajectory. So obviously this ellipse as a geometrical shape possesses some features which we need to highlight here. So first one is the so-called major semi-axis, which is A. So from center of the ellipse to its like extreme point, like furthest point from the center. And also there is some distance between the center and the focus. C, bless you. So there is such parameter as an eccentricity of ellipse, and that is E equal to ratio C over A. What would be eccentricity of a circle? In the other extreme, it will be unity. For eccentricity for a circle would be equal to unity, because for a circle we don't have two focus, we have one focus which is in the center, means distance between the center of the geometrical set of points and to the focus will be equal to 0, because focus will be in the center. So C will be equal to 0, and then we get A would be equal to radius. But in any way, 0 divided by any number would give us 0. So eccentricity in general changes from unity to 0. And what we need to highlight here, that for majority of planets in our solar system, we have this eccentricity quite close to unity, means that the trajectory is close to circular trajectory. However, it's indeed not the ideal circular trajectory. Okay, so here we define what is ellipse and how we can quantify it. Then what is the second Kepler's law? What does it tell us? So in let us maybe draw it to have some graphical representation also. So this is our sun here. Here is our planet at some initial moment of time t equals 0. So here is the position vector r, which defines position of the planet with respect to the center of the sun. Then in some time interval dt, this planet will move here. So this will be new position vector. And here we will have dr, change of position vector. So what second Kepler's law tells us? That the area which is swiped off with this, like covered by the changing position vector over time will be the same per unit time, no matter where this planet will be located. So it may be here, it may be here, here, no matter where t0 we pick up, like initial moment of time, per unit time area, which is divided by this position vector, will remain constant. So that is the second law of what was formulated by Kepler, yes? That actually means that it doesn't have constant velocity, because let us then focus. Let's put it a little bit lower. So again, as a disclaimer, we explain this based on angular momentum conservation. So what happens when position vector is changing? Linear velocity vector is also changing, not only in orientation but also in magnitude. So where we have extreme points, where the planet is closest to the sun is here, and planet is furthest to the sun. So when it's closest to the sun, velocity vector magnitude is large. When it's further, it goes here, velocity vector is small. But when we calculate this area, we need to consider two vectors, r and dr. So if this guy is small, then dr will be large, because velocity vector is large, velocity times dt will give us large dr. If this is large, so where planet is located here, dr will be small. And when we combine all this, eventually we will get that it actually does not depend where the planet is located. Per unit time, this area will be the same. So let us explain this from the point of view of conservation of angular momentum. So let's draw another ellipse here, or something what can be considered as an ellipse in first approximation. Here we have a planet MP. Then this is gravitational force, and this is velocity vector of the planet. Now, tell me, what do you think? What will be the net torque exerted on planet in this system, Sun, planet? So we remember torque, it's F multiplied to the R, which or D, what is considered as the lever arm. And in this configuration, when we deal with so-called centric force, gravitational force is pointed to the center of the sun. What will be the lever arm? 0. So means that for this given system, there is 0 net torque exerted on the planet. So we can write here, this is equal to 0. What is the relationship between net torque and angular momentum? That's correct. That's conservation of angular momentum, but the relationship actually between the net torque, it will be first derivative of angular momentum over time. So from here we can make a statement that this is equal to 0, because we know that net torque is equal to 0. And since first derivative over time is equal to 0, then L, the angular momentum, is constant. So that is the conservation of angular momentum. Now let us recall what is the definition of angular momentum. Angular momentum is cross product of position vector and linear momentum vector. So how we express linear momentum vector? So it's mass times mass of the planet times velocity vector. So we can write here mp times cross product r and v. So this we keep in mind. Let's put it in parentheses. And now let us come back to our first figure. And this dashed area we will call dA. So how we define this dA? Based on the definition of the cross product between two vectors, if we pick up r vector, position vector, and dr vector. So that will be area of this parallelogram. So means the area which is covered by moving position vector in this time interval dt will be half of this area. So we can write that dA is equal to 1/2 of r vector cross product dr vector. How we define this dr vector? A change of position vector. That is velocity vector times time. So we can write the dA. Oh, and here we can just take magnitude because we don't care about the orientation. So dA is equal to 1/2 magnitude of r vector cross product v vector, and here will be dt. So now we look at expression for angular momentum and this area, and we see similarities. So we can actually express dA in terms of angular momentum, L. Of course, in terms of like magnitude, we don't operate with vectors. So that, for that, what we need to do, we need to multiply and divide by mp. So if we have mp here in numerator, 2mp here, then we have absolute value of r vector times v vector, and here is dt. So eventually we get that this part will be L, angular momentum, magnitude of angular momentum, divided by 2mp n times dt. So this is the definition of dA. So remember what third law, Kepler's law, tells us, that area covered by this moving position vector per unit time. So we actually need to consider the rate of area changing. So that will be dA over dt, and that is equal to L divided by 2mp. So now look at the right side of this equation, and what we have. mp is constant, it doesn't change because mass of the planet doesn't change. Then we have angular momentum, and previously we claimed that for this system angular momentum is also constant. So we have two constant parameters, so eventually this will be equal also to some constant. Means that dA over dt is equal to constant. That is actually the expression for the second Kepler's law. It tells that rate of covering area by moving position over time remains constant no matter where the planet is located along this ellipse trajectory. So now we are done with explaining the reasoning behind second Kepler's law, and we move to the third. So what third Kepler's law tells us? Orbit and period relationship. So to be short, it is t square is proportional to a cube. So period of moving about the sun is proportional to the cube of the semi-major axis of this ellipse. As I mentioned earlier, most of planets, they possess trajectories very close to circular shape. So let us consider some simplified case when we have sun and circular trajectory of a planet about this sun. So then what we have a planet, so this is ms, this is mp, we have some velocity vector v and some position vector r. Now look at this figure and tell me under which condition, like what should be true when we have this trajectory and this is a stable trajectory. So over time it doesn't change, it doesn't go neither further nor closer to the sun, it stays on the same trajectory. What forces are exerted on this planet? Let's consider this planet here. So here will be gravitational force, and in order to counterbalance it, here should be centrifugal force. So instead of centripetal force, we put just highlight that it's different. Let's put it S here. So it's this apparent force which tries to move away planet from its orbit, and it's compensated by the gravitational force. So now, in order to have equilibrium condition, we can write that Fg is equal to mp, mass of the planet, times centripetal acceleration, AC. We can express it in different form. So we know from universal gravitational law that gravitational force will be G times ms times mp divided by r square, and that is equal to mp times v square over r. So mp we can cancel out, square and this r we cancel out, but you see that third Kepler's law operates with the period. So we want to do some manipulations here with velocity vector in order to express it in terms of period. So how would we do that? Linear velocity will be equal to circumference of this circle, 2 pi times r, and divided by period t. So now we can substitute it here, and we get the following: G times ms over r is equal to 4 pi square times r square divided by t square. From here, we can express T square is equal to 4 pi square over GMS times R cube. Or it can be some constant k times R cube, where constant k is 4 pi square over G times MS. If we operate with planets in our solar system, this is a constant because mass of the sun is considered to be a constant, which in first approximation true, but to be precisely saying about this, it's actually not true. Mass of the sun is reducing always. By the way, any suggestions why mass of the sun is shrinking? That's one source, but actually not major one. So yes, energy, photon energy can be converted to mass loss. There is another reason, which is the dominant one. Have you heard about solar wind? That's hot protons, like mostly protons, from the surface of the sun, which are ejected in the space, and they just move in the space which surrounds the sun, means our solar system, causes this aurora effects in northern and southern poles. We can see this lights in the sky. So all these effects are originated from solar wind, and they can also damage electronics in space. And well, even when you travel over with the airplane, the level of radiation increases quite a lot because we are closer to the outer layers of atmosphere, and these particles cause some interaction with the environment, which is not favorable for our organism. So, but of course, this change is quite small and was relative to the mass of the sun, so it's considered to be constant in first approximation. So what we have here, that T square is proportional to R cube, because this is a constant. So that is true for for circular trajectory, but that's a simple explanation. However, if we extrapolate this to ellipse trajectory, also the same principle. Stationary condition should provide us the equilibrium between centrifugal and gravitational forces. That will be also true for semi-major axis of ellipse. T squared is proportional to a cube. What is important here, that for this equation for T squared, we don't have mass of the planet. So here we have mass of the sun, but not mass of the planet. Means that this can be translated to every planet in the solar system, no matter which mass is it. Again, looking to this equation, you may already see a simple way how we can estimate our sun's mass. We cannot measure it directly, but if we express mass of the sun from this equation, so it will be ms equal to 4 pi square over gt square r cube. So then we can easily measure period of rotation for Earth, for instance, it's 1 year, we know it. For other planets, we can calculate also quite straightforwardly. And we can also measure distance. And with this simple relationship, we get expression for the estimation of the mass of the sun. So now let us use all this information about Kepler's laws and second law of motion, and let us show step by step what was indeed that apple which fell on Newton's head and how he came up to this universal gravitational law. Apparently that was not apple, that was a combination of these three laws. And it will make sense for you after we go through it. Again, we consider some simplified case when we have circular trajectory, because that actually quite reasonable approximation for majority of our planets. And we remember that the third Kepler's law tells us the following: T square for circular trajectory is proportional to r radius cube of the trajectory. So in other form, we can write that t square divided by r cube is equal to some constant. So this we keep in mind. And then we recall again how we define centripetal acceleration. That's acceleration which planet experiences while it's moving along circular trajectory. So that is linear velocity square over radius. From here, we can also like represent it in terms of period because we want to have a connection to the third law of motion. So it's 2 pi r over t, that will be linear velocity. And eventually we can write that centripetal acceleration will be 4 pi square r square over rt square. So r square we can cancel out, so it will be 4 pi square times r divided by t square. So now, according to the second law of motion, we have centripetal acceleration can be expressed as centrifugal force divided by mass of the planet, mp. And we also know that it can be expressed by this equation. So it will be equal to 4 pi square times r over t squared. So now we need to mention that by magnitude, centrifugal force, since we deal with equilibrium condition, should be equal to gravitational force. That's what we discussed previously. Means that we can substitute Fs with Fg, and since they are equal by magnitude. And before we do that, let us multiply left and right side of this equation by r squared. So now we have Fg already instead of Fs over mp times r squared. That will be equal to 4 pi squared r cubed over t squared. So what you can tell me about the right side of this equation? This part, it's the acceleration. Well, it was acceleration, centripetal acceleration, before we multiply by r squared. Now it doesn't give us exactly some parameter. What? No. It is actually some constant, because as we discussed at the beginning, according to third law formulated by Kepler, this ratio is a constant. So here we have like flipped over ratios, r cubed over t squared, but it's still constant. Pi is constant, so we have actually this ratio gives us constant. Pi is constant, means that the right side of this equation is equal to some constant. So now, if the right side is equal to constant, the left side is also equal to this constant. So from here we can write that Fg over mp times r square is equal to constant. And we come to this point when we can already express gravitational force. That is some constant times mp divided by r squared. So that is not yet the final form, it's getting closer. But let us think about this constant. What is hidden there at this point, what we already actually know. There is something what we don't know, but there is one parameter which we know, and we can kind of extract from this constant. We know that gravitational force depends on mass of both objects. So if we operate here with mass of the planet, obviously here should be in this constant hidden another parameter which states for mass of the sun. And we can take it out because let's say we know mass of the sun. So we come up with some constant c, new constant, let's call it constant c. Then we have ms times mp over r squared. And this constant c, which we came up with, that is gravitational, universal gravitational constant g. And this is the form how Newton actually wrote, derived, based on combination of three laws. Second law of motion, which he proposed based on empirical observations. Then two laws of which were formulated by Kepler, also based on empirical observations. And this is an example how Newton managed to combine all these empirically obtained laws which describe behavior of nature around us and develop a model. So this universal gravitational law is actually not based on some observations. He derived it by using the known information about nature formulated in these three empirical laws. And as you may remember, it was written in this form, but this constant g was unknown for quite a long time. Took over 100 years to get its numerical value. So apparently that was not an apple, but first of all, his major contribution when he made the statement for second law of motion, the relationship between force and mass and acceleration, and also this 16 years of crazy work by Kepler and Brother, observing this motion of planets with respect to stationary stars, hundreds of stationary stars, and analyzing this huge pile of data in order to formulate the statement for these three Kepler's laws. Based on their contribution, combining with second law of motion, Newton actually came up with the universal law of gravity, which actually we use now. We use this universal law, like classical form of universal law of gravity, in order to calculate orbits of planets, asteroids, satellites, and so on and so on, within this macro scale of the solar system and beyond. it works quite well, and accuracy is enough to give us the predictions, very accurate predictions of how our satellites will uh, move to different planets or beyond the solar system. So let us summarize our discussion for today. We continued with the discussion of Kepler's laws. Um, Besides introducing the formulation which was um, provided by Kepler, we also explained the physics behind these statements. And for instance, when we deal with the second Kepler's law, we understand that the reason for that this position vector covers equal areas per unit time, no matter where planet is located, is because, first of all, gravitational force is a centric force. It does not provide any net torque on the planet. That means that net torque is equal to zero, means that the angular momentum of the planet remains constant. And based on the conservation of angular momentum, we can show that indeed this area per unit time is constant. For third Kepler's law, it actually results of the second law of motion, which states that for equilibrium orbit, gravitational force should be counterbalanced with centrifugal force, and we could express both gravitational and centrifugal force, express linear velocity vector via period of rotation, and then have the relationship between period of rotation and radius of the trajectory. And what I believe is quite important, we have shown how these three empirically obtained laws based on experimental observations were served as the basement for Newton to derive the expression for universal gravitational law. So with this, we continue our discussion of gravity next lecture. That there we will introduce the concept of gravitational field and strengths of gravitational field, because so far we claim that there is interaction between two objects and there is some gravitational force, but the biggest question in Newton's time, when he introduced the universal gravitational law, what is the mechanism? How it's possible that two objects located somewhere in vacuum, there's no medium, nothing is around these two objects, but they still can interact with each other, because our everyday experience tells us that in order to have interaction, there should be a physical contact between two objects. So there should be some collision, then interaction happens. But now we have interaction without a physical contact between two objects located somewhere in vacuum. So in order to explain that, we introduce this concept of gravitational field. So that will be for our next lecture on Friday. To see you there. Thank you very much for your attention. Have a good evening.